Hi, I'm Dan Reynolds. I'm one of the lead developers of the sundials team, and I'm going to talk about time integration and nonlinear solvers. And that's going to be kind of generic for all, maybe not all, but many time integrator libraries. And then I'll focus on our hands-on exercises on using sundials to do a lot of these time integration exercises. My plan is to have the first 15 minutes be kind of overview stuff, and then the last 45 be 3 hands-on exercises. We're going to break for lunch in the middle, though, so it'll be lecture plus a hands-on, then lunch, and then we'll come back and do 2 more. From the earlier this morning, when Mark had everybody raise hands, it looks like many of you come from applications. So some of this might actually be some of the more introductory material here will be relatively informative, I guess. Those of you who have had numerical ODE classes and stuff, bear with us through some of the introductory material. Okay, so. Time integrators in general and nonlinear solvers arise when we have time derivatives inside of a problem. And so just to kind of set the stage really simply, in general, most models of physical systems are formulated based on the rate of change of something. And so if U is this something we want to understand, then we can have its derivative with respect to time. And so, for example, Newton's second law, force equals mass times acceleration, is often rewritten in many simulation codes as dv dt is equal to some set of forces. Similarly, if there's a number of chemists in the room, you guys have your chemical rate equations where you have 2 reactants A and B that create a product P. And so that can be written down as an ODE. So the derivative with respect to time of the chemical concentration of the product is given based on the concentrations of A and B to begin with. And time integrators are really there to help you track the temporal dynamics of these systems of equations as your simulation proceeds. And so, for example, on the bottom I have some snapshots of what's called a sawtooth reconnection in a tokamak fusion reactor. And you can just see, it's not necessarily you care about a steady state, but you really want to see what happens when you go from the beginning to the end. And you really care about getting an accurate solution as you go through these kinds of calculations. So where do they fit in this hierarchy of software? So unlike a spatial discretization that kind of lives, I would think, kind of at the bottom of this hierarchy that defines your data structures and how you even store things, or visualization that might happen at the top after you've run your stuff, how do you look at the results? Time integrators and nonlinear solvers often kind of live in the center, in that we don't want to tell you how to store your data. We're not going to tell you how to visualize your data, but we want to help you solve that problem that you have defined on that data structure that you're looking at. And so, for example, 2 PDE systems that are solved a lot. On the left, we have the compressible Euler equations, and on the right, we have the incompressible Navier-Stokes equations. And on the left, we see that every one of these PDEs has a time derivative on something, be it the mass, the velocity field, or the total energy. Whereas over here, we have a time derivative on U, but we have a constraint equation that has no time derivative at all. And so both of these correspond to systems of evolution equations. In general, when people discretize these using what's called a method of lines approach, you do AMRX or whatever you're going to do in space, kind of like Mark showed you this morning with the discretization in space of the 1D heat equation. And after you've finished discretizing in space, if you gather all of your unknowns, all your densities, velocities, energies, everywhere throughout your domain, and you call that big vector Y, then this guy on the left is going to be a standard ODE. So a system of ODEs, dy dt, is equal to some right-hand side, where F encodes all of your physics, encodes all of your spatial discretization, encodes all that stuff. But you've got this ODE system that's enormous that you want to track as a function of time. This one on the right, notice because the unknowns here are U and P. We don't see a P down here. There's no dp dt. And so this is what's called a differential algebraic equation. We have an evolution equation for the velocity field, but the pressure has to be solved for as a constraint. And so we usually do the pressure in a constraint type formulation as well. And so that gives rise to what's called, I mentioned before, a differential algebraic equation. We have a mixture of time-dependent equations and just algebraic equations that need to be solved. And so here's a standard way we write down a DAE. When solving these things with implicit discretization, which I'll talk more about a little bit later, or even if you didn't want to do time integration at all and you just want to go straight to steady state, so steady state means that all of these time derivatives are equal to 0, you end up with a nonlinear system of crazy equations that have to be solved altogether. And so we write those down as some big F of a set X of all your unknowns, and you want to set that equal to 0. And so I'm going to try to focus on both of these 2 topics. Nonlinear solvers come up in time integrators, and that's why they kind of group them together in this lecture. Okay? So as we saw with Mark's hand-coded heat example, a standard thing that we do in high-performance computing is time marching. And so we define our unknowns as a function of time, and we only want to know those values at snapshots. And so given times tn, we want to know our state y sub n. We have time step size delta tn. This is going to be indexed because we could allow adaptive time stepping, so little time steps, then big time steps, et cetera. And we only want to know our solution at these snapshots. So these time marching schemes will compute the new solution, yn plus 1, using some formula that depends on the time step size you're using, the old data, yn, maybe previous ones, yn minus 1, yn minus 2, et cetera. And maybe it also depends on the thing you're trying to compute as well. And so we're going to, this increment function phi will encode your time stepping approach that you're trying to take. So 2 textbook examples that everyone learns, maybe the first 2 examples that they see, are explicit or forward Euler, where the new solution is just the old solution plus delta t times f. And so if we go back one slide, we can see that if you take y at n plus 1 minus y at n divided by delta t and set that equal to f, and you move the delta t over, you get exactly this forward Euler approximation. Similarly, implicit Euler, yn plus 1 is yn plus delta t times f, but now f is evaluated at the new solution you're trying to compute. And so this is going to be an explicit method and an implicit method, just these archetypes of what these kind of classes of integrators look like. In general, we can have all kinds of explicit integrators, implicit integrators, even mixed implicit-explicit approaches called IMEX approaches. And in general, the way we categorize them is we ask, what does phi depend on? Specifically, if phi depends on the new solution, like we have here, then there's a nonlinear system that needs to be solved. We need yn plus 1. We can't just compute the stuff on the right because it's also on the left, and so this defines a nonlinear system of equations to compute. On the other hand, if phi does not depend on yn plus 1, so like here, the yn plus 1 is just explicitly computable based on previous data, it's an explicit method. And so this general categorization of explicit versus implicit, many of you already know, but this is kind of where that name comes from. And these IMEX type discretizations are based on formulations where maybe some pieces of the physics depend on yn plus 1, and other pieces of the physics don't depend on yn plus 1. You can kind of mix and match as you see fit, and we'll see more about that a little bit later. So time integration methods that aren't forward and backward Euler can achieve high order accuracy in a number of ways. So the 2 basic classes, so there's many more, there's going to be one-step methods versus multi-step methods. And so a one-step method is like a Runge-Kutta method or a Rosenbrock method, if you've heard of those names before. And the basic premise is you start with your solution at yn, and you do lots of work, potentially, for a very high-order scheme to get yn plus 1. But you don't need a long history of old data. A multi-step method, on the other hand, you want to get yn plus 1, well, you need yn and yn minus 1, yn minus 2, yn minus 3. You need a lot of your historical data to help get you this higher-order accurate solution as a function of time. And so if you've heard of Adams-Bashforth or backwards differentiation formula methods, that's the kind of classes those come from. A fundamental concept that you saw with the hand-coded heat equation, but you didn't really play around too much with it, is this question of stability. Mark had this if statement. If this R thing was greater than a half, just fail before you even get started. And that comes from this concept of linear stability. And so a lot of people kind of maybe misunderstand what linear stability really is. And the basic premise is it's a question of, for a desired step size that you want to take, what happens to floating point round-off error? So every calculation you ever do always has round-off error. Does that round-off error grow without bound? An unstable calculation. Or is that round-off error controlled? And so that's going to be a stable calculation. And so for those of you who haven't kind of seen how linear stability looks in the context of time integrators, I'm not going to teach it to you, but there's 3 slides at the end of this deck. If you click this link, it'll take you there. You can read a little bit. It's the standard kind of stuff I teach in my intro undergrad class on this topic. Okay? So that said, there are some methods that are going to be linearly stable no matter what time step size you throw at them. Any time step size you want to use, it'll always work as far as stability is concerned. And those are called astable methods. They're only possible with implicit methods. There's a caveat to that. There's these things called exponential integrators that are technically explicit and also astable, but they involve so much work per step that they might as well just be an implicit integrator in the first place. Non-astable methods, like all explicit methods, there's going to be some maximum time step size that you can take. that in the hand-coded heat, that had to do with that R factor. And this question of what's that biggest step size you can take before round-off errors grow out of control is this question of this stability boundary. In PDEs, it's often called a CFL for Courant, Friedrichs, and Levy, who invented it, I don't know when, a long time ago. But it's typically in hyperbolic and parabolic equations, something like the time step size is proportional to the spatial mesh size or the spatial mesh size squared. If you're unfortunate enough to work on hyperdiffusive equations, maybe it's delta x to the fourth, et cetera. But these are going to define how the maximum step sizes you can take for stability. And I'll note that especially in an audience where people aren't all mathematicians, I really need to drive home the point that stability is not the same as accuracy. I interact with a lot of people, and if it doesn't blow up and they get a pretty picture, they consider it success. It might be completely wrong, but as long as they get a pretty picture and it doesn't blow up, they think it's perfectly fine. Stability just means you don't get ifs and nands. It doesn't mean that you have even a digit of accuracy in your solution. And so remember that when you leave here, you don't have to use everything I'm going to talk about, but just remember, just because it doesn't blow up doesn't mean that it's right, okay? Okay, so how do you choose between an explicit and implicit method? There's some general kind of things to think about. Explicit methods are really easy to kind of conceptualize. They're easy to code. There's no algebraic, nonlinear, or linear solvers necessary, but they're going to have an upper bound on the stable step size you can take. And if, for example, your problem many multi-physics type applications, there's really fast things and there's slower things. And maybe the thing you care about is not the fastest possible thing going on in the problem. That fastest thing will set that maximum time step size. And so if you care about a slower thing, you're going to be wasting a lot of effort taking tiny, tiny, tiny time steps. An implicit method, on the other hand, might have no stability limit or much looser stability limits. They allow you to step over those fast kind of parasitic dynamics if you're uninterested in them. But they definitely require some kind of solver, some nonlinear or linear solver that's going to couple everything together through your whole exascale calculation. All the nodes are suddenly coupled together to solve this problem, potentially. And so that really increases code complexity if you're writing this from scratch. IMEX methods use a bit of both. And so the idea there is you take some parts of your operator and you treat those implicitly to get past, to handle the stability conditions that come from those. If that piece would require a super tiny time step size. Whereas you might make other pieces explicit because that would really kill a nonlinear solver. It would be so hard to solve those algebraic equations, maybe if you can treat that explicitly or whatever. There's an art form to it. There's no standard simple rubric to follow to make it happen. So stiffness is typically this thing that helps us make our decision. And so two of the kind of giants in the field a long time ago defined stiffness in I think, a really excellent way. And that is that if the time step size you need to make forward Euler be stable is much, much smaller than the time step size you would need for forward Euler to be accurate. So let's say for accuracy, a time step size of 10 to the minus 1 would be fine. But for stability, you need a time step size of 10 to the minus 7. You're going to waste a lot of effort just maintaining stability as opposed to getting an accurate answer. And so this can depend on all kinds of stuff. Eigenvalues of the Jacobian of the right-hand side, the size of the problem, the accuracy you're looking for, all kinds of things. Yeah, I like this italicized thing because it's a nice, easier way to think about it. And I'll note that if you're solving a differential algebraic equation, you pretty much just have to use an implicit method because they're super stiff. Okay, so stability alone shouldn't dictate the time step size that you use in your application. So given a maximum stable step size, adaptive time stepping methods pick the delta Tn so that it gets the accuracy you want. So let's say you want 2 digits of accuracy in your solution. You don't tell us to take 700 time steps or tell us to take time step sizes of a fixed size. You just tell us how accurate you want those answers to be. And we'll adapt that time step size accordingly to get as fast as possible the answer with the accuracy that you seek. And so the basic premise is that each step we compute both a solution and an estimate of our error that's induced in that step. If that error is too large, we throw out that entire time step and recompute it. If that error is small enough, we accept it and then pick a new time step size so the next one will be as big as possible but will still meet the accuracy requirements. And so temporal adaptivity can lead to much more efficient and accurate results than if you just use a fixed time stepping kind of approach. So I work with the sundials team, and so I'll just mention kind of the way that we think about problems. Then the next slide after this, I'll talk about a couple other packages that also have time integrators in them. So we like to think about the problem you want to solve, and then we have different packages that are used to solve different types of time-dependent equations. And so CVOTE is the most well-known package inside of sundials. It uses linear multi-step methods, and it thinks of ODEs in kind of standard form. Argonne is the one that I created, and so it allows you to split this right-hand side into implicit and explicit components, or even now into fast and slow for multi-rate type simulations. IDA is a differential algebraic equation solver. And the way that we think about error is we think about adapting our time step sizes so that this metric, which you don't have to memorize, is less than 1. And basically what it really says is we have two inputs that are really of importance. A relative tolerance, which is a scalar, and it's how many significant digits do you want. If you want 1 digit of accuracy, give us an RTOL of 10 to the minus 1. If you want 2 significant digits, give us an RTOL of 10 to the minus 2, etc. And ATOL tells us if some solution components have different units than others, what's small for a given solution component. So if density wants to have values in the order of 1, then 10 to the minus 9 is a pretty small noise level value. But if your momenta or velocities have speeds of 10 to the 5, then 10 to the minus 9 is really, really tiny, close to round off. So maybe 10 to the minus 2 would be a reasonable absolute tolerance for those quantities. So it helps you encode the units of your simulation. PETSI has a TS module that does similar kinds of stuff as what sundials does. They think of all problems in the exact same way, so you code it up once so you can try out everything on it. It means that it's more flexible, but maybe they can't squeeze out quite as much efficiency from this formulation. F holds the stiff portions, G holds the non-stiff portions, and they have Runge-Kutta-like integrators built on these kinds of things. Trilinos has a Rhythmos package, which uses linear multi-step methods. They're building something called Tempest, but I could not find a single piece of information online about that. But it's essentially modeled very similarly to Argonne, and I've talked to the developer who's building it now. Maybe some Trilinos folks can talk about it later if you have questions. All of these packages will do time additivity for you, and they're all hooked up to lots of algebraic solvers for nonlinear linear systems, so you don't have to write all that hard stuff yourself. So nonlinear solvers in general must be iterative. So since most nonlinear equations don't have analytical solutions. And basically the premise there is you start out with an initial guess, x naught, and you iterate until the norm of f, remember you want f to equal 0, until the norm of f is small, you have some update formula. Two basic categories are fixed point versus Newton iterations. Fixed point methods are usually rather simplistic. They don't converge very fast, but they can have a large domain of convergence, so they can be really robust. Whereas Newton methods converge really fast, but they can have a really small domain of convergence, and so you have a trade-off. And these guys, which are kind of the core of most large-scale solvers, wrong button. They use the Jacobian of f inside their calculations. And so if you notice this formula, if f is vector valued, then j is matrix valued, so this is a linear solve. So inside of a Newton-based nonlinear solver, you need to do large-scale linear solvers, and that's going to be the focus of the next set of lectures after me this afternoon. And so for most problems, Newton's method is algorithmically scalable. A coarse problem might take 3 Newton iterations, and a superfine mesh on an exascale system might still only take 3 Newton iterations. But what they really require is a super robust and scalable linear solver to handle that solve right there under the hood. Okay, so there's a lot of nonlinear solver packages that are also available. So we have a Kinsol package inside of sundials. PETSI has SNES. Trilinos has Knox. And all of these have so many bells and whistles. I didn't even put them all up here. But they're much fancier than the things that you would write just to kind of solve something on your own. So why use a solver instead of rolling your own? Lois talked about this a little bit earlier. Many applications just start out and they want to do everything themselves because they want to have complete control. And I understand that. But while it can work, those might be really simplistic, like straight out of a numerical recipes book. They might be buggy at first. They almost certainly don't have any of these advanced expert features that come from libraries. Whereas these libraries, on the other hand, are going to be typically bug-free, though if you find a bug, let us all know. Heavily tested, they have a lot of benefits involved. We all do time adaptivity for time integrators. They seamlessly integrate with algebraic solver libraries, and they include a lot of optimizations that you might not want now, but you might really need later, like optimization and derivative information, et cetera. So for more information, follow any of these links, and you can go to all of their websites. So we have 3 hands-on lessons. The first is going to focus on explicit time integration, then lunch, then 2 after lunch. And so let me switch over to that. If you had done the rsync that everybody talked about before, you don't need to do it again. I haven't changed anything. Right, so if you've rsynced everything already, that's great. Then you're going to CD into the Hands-On Lessons Time Integrator Sundials folder. And inside, there's a SH file I'd like all of you to source. We're building all of these time integrator stuff right on top of AMRX. And Don had some nice tools in there that allows us to do error calculations between different solutions. So if you also run this source file. And if you don't have the Anaconda 3 soft-end environment already loaded, please add it. Even if you don't know if you have it, go ahead and do the soft add anyway, and then you'll definitely have it. We're going to run some Python to make some pictures of things along the way. So our problem is actually very similar to the one that AMRX did their first one. We have a contaminant inside of a domain, and we have an advection field that's going to push it. Here we don't have some fancy curly advection field. We just have advection in a single direction. But it's going to be an advection diffusion problem. So we also allow this to diffuse in space as time goes on. This is going to be modeled by this PDE shown here, dudt plus a dot grad u minus the divergence of the diffusion tensor times grad u. And so the basic important parts here is that we have advection and diffusion, and those are going to have different stiffnesses with respect to how we might need to use an explicit solver to work on them. So there's a lot of code in this folder. All the executables are already built. If you want to build them again, you can just type make, but you don't need to. Though if you do one of the nighttime hands-on, you might change stuff and rebuild. Right. So for some snapshots of what happens, this is going to flow kind of off to the top right and get it's going to spread out because it's diffusing a little bit. So it's not a super pretty picture, but that's okay. All right. So let's see. So for any of these executables, you can ask for help. So if you say the hands-on one, if I can type 1.exe and then help equals 1, you'll see the set of command line options that are available for each of these executables. They build in complexity, so hands-on 1 has fewer options than hands-on 3, et cetera. And you can see what the default values are for each of these. I'll ask you to do some things as you go, and if you forget what a command is, you can always ask this to figure out what the names of these are. And so the first thing we're going to, I'm running a little short on this time period, so I'm gonna not kind of go through the way that we hook AMRX to sundials, aside from just saying that we don't have them copy their data to us at any point. We act on the AMRX data directly. And if you want to see how you build that kind of interface, just to teach sundials how to operate on your data, there's some, I mentioned where to look inside of here for that kind of thing. So it never involves copies, and the reason being that would make things so slow and inefficient that nobody would ever use sundials in the first place. There are packages that do require data copies, but they give you a lot more on top of that, so that data copy, is acceptable or palatable. So some information on how we teach sundials how to do this stuff is here at the beginning. But now let's run this hands-on one with the first set of inputs 1, and just see what we do. So this is going to run a problem that uses 128 squared mesh, a time step size of 5.0. So this is fixed time step sizes in this problem. And it finishes. It takes 2,000 internal time steps to go to our final time of 10,000. There's some statistics down here about what happened when it ran, et cetera. And to compute error, I've made a reference solution that it's not an analytical solution, but it's a really accurate one that we can always compare against. And so if you do this fcompare .gnu.ex plt01 reference solution, then this is one of these tools that Don built, or Don pointed me to. He might not have built, I don't know, but that allow you to see the accuracy at the end of this simulation in that computed solution. So with a fixed time step size of 5 units, seconds, whatever, we get a super accurate answer, 10 to the minus 9. So that's kind of nice. Okay. So let's run it again, but let's run it with a bigger time step size. So we can do that with a fixed DT of, say, 100, and it runs way faster. So, already we're really happy because we had a 20 times larger time step size and it ran at about 1/20th the amount of time. But then if we look at the accuracy, we see that the error is 10 to the 98. So it's not nan, and it's not inf, but it might as well be a nan or an inf. Okay? So did anybody tell me what happened? You don't have to. There's a Google form, but you don't have to. What's happened? It was an unstable time step size. So we certainly can't use a time step size of 100 for this advection diffusion problem with fixed time stepping. Okay, so we can turn on temporal adaptivity, which is technically our code's default, but I didn't do that here. I made the default be fixed. But if we tell the executable use a fixed time step size of 0, then it says, all right, let's let our code do what it wants to do as far as time adaptivity is concerned. And so it runs. It's still pretty fast. It took less than a second. And when we check our error, we see that our errors are in the order of 10 to the minus 6. Okay? So when we ran this, as I mentioned earlier, we want to know how accurate you want the answer to be. And so the two inputs that were there, these are the defaults, were a relative tolerance of 10 to the minus 4 and an absolute tolerance of 10 to the minus 9 on this simulation. And we see that the answer we get is pretty much 10 to the minus 5. So it's a little bit smaller than the relative tolerance that we specified. It's a pretty good answer. It's not way over solving the problem, et cetera. Okay? And so if we want to see what happened internally, we can do this process arc step diags hands-on 1 diagnostics.txt. This doesn't actually do that much, but for some reason on Cooley it takes a while to run. But inside this executable, I have it actually output everything our code did as far as time stepping was concerned on every internal time step, the error estimates it had, et cetera. And so that got saved to this file, hands-on 1 diagnostics. And then this is a Python script that loads all that data and makes some plots and stuff. And so what we see is that the average time step size that it took was about 21.9. The maximum time step size it ever tried was 35.2, and it had 24 failed time steps, et cetera. And so if we want to see what it looks like, we can say display h versus iter. I'll note there was one of these hands-on things I was going to have you guys actively try to figure out what the biggest time step size you could use was, but I talked too slow earlier. But what we see here is that what happens is we start out, our code always starts with a really small initial step size to be conservative. It doesn't like failing right out of the gate. But really, really rapidly, it gets up to essentially the CFL condition. So it finds that dynamically without you having to know what it looks like, et cetera. Every now and then it tries to take bigger time step sizes because it doesn't know that this is a problem that's going to have a fixed CFL condition. And if in many applications, that CFL condition changes dynamically as a function of time, and so it might want to increase that step size kind of as it goes. And so it's going to try every now and then, and it gets kicked back as a failed step. And so all those X's are those failed steps that we come back and we maintain right where we're at. And so instead of you trying to figure out with a fixed time stepping method by experimentation what's the biggest step size you can take that's still stable, et cetera, our code found it essentially for us for free. Okay? All right. So if you'd like, I recommend it. Try running with different values of RTOL and see. So this had an RTOL of 10 to the minus 5 was the default for this executable. Try out different values and see how the overall number of time steps changes and maybe the solution accuracy changes. So we took 457 for an accuracy of essentially 10 to the minus 5. And with a relative tolerance to 10 to the minus 4. So you could try out relative tolerance to 10 to the minus 8 or 10 to the minus 2, et cetera, and kind of see how that changes. Okay? So the last thing I want to do is you can keep playing with the relative tolerance and stuff as much as you like, but the last thing I want to do is show you a nice feature of libraries that most people don't ever get when they do it by hand, and that is that you can swap out which method you want kind of on the fly. And so the default method we had in there was a explicit Runge-Kutta method of order 4. Our code has explicit Runge-Kutta methods and implicit Runge-Kutta methods and additive Runge-Kutta methods, et cetera, just all over the place. And you just tell us what the order of accuracy you want is, and there's a default for that order of accuracy. And so the explicit methods in our code have orders 2 through 8. So let's just try it with a relative tolerance, so with the order 8 method. And so we see that, just to point out 2 things. So here we took 258 time steps with the 8th order accurate method. With the 4th order accurate method, we took 457 time steps. So it's pretty well known that with Runge-Kutta methods, when you go to higher and higher order, the stability region increases and you can take larger step sizes. So you'd think big win, you took half as many time steps. But we have to work harder within each step with a higher order method. And so the real question is actually how much work did it have to do? So here for the 4th order method, 2,800 right-hand side function calls to do the 4th order thing. But for the 8th order one, it took 3,700. So it took more work at the end of the day, even though it got to take larger time step sizes to use this higher order method. The optimum, which method you pick, which order of action you choose, is going to be highly problem dependent. So some physical problems, the solutions aren't sufficiently differentiable to allow it anything higher than a 3rd order accurate method anyway. So you can try these things out and figure out what's best for your application without having to look things back up in textbooks or on papers and recode them all yourself, et cetera. You can play around and figure out what's best for you as you go. So, feel free to try out the R code order value for this explicit thing and the relative tolerance, and see how those things kind of work together and play together nicely. I'm going to be done for now, so we can go to lunch. But when we come back, we're going to switch from explicit methods to implicit methods and IMEX methods. And so, if you have any questions about these things, feel free to hunt me down at lunchtime or whatever. But any questions? Yet? Was there a hand? Jacob?
Yeah, so what data structures do you require to use under the load? So like say I have some memory allocated on the GPU, can your...
Yeah, so we don't care how you store the data at all. What we need is to be able to ask you to do things. So we might say, please take the dot product of 2 vectors and give us the scalar output. Or please add this vector to this other vector with this linear combination coefficient. And so if your data is on the GPU, then we'll need to be able to pass those coefficients for the linear combination from CPU to GPU. We're driving it at the CPU level. We are working on some of these where everything, even all of our logic, lives on the GPU, but we're not quite there yet because logic stuff doesn't like GPUs very much, or other way around. But yeah, as you can do, we have example vector kernels that live on GPUs, that we have Raja vector kernels, all kinds of stuff. So I'm not doing an overview of sundials here, but yeah, you teach us how to act on your data,
so
and we're good.
So it's just like a CPU or a class, and I just have to fill in all.
Except it's in C, but yeah, think about a C++ class written in C, if you can kind of get your head around that. Yeah, we like portability, so it's all in C, but it's essentially a C++ class. Other questions? All right, bon appetit. All right, so I apologize that we went kind of quickly through the hands-on one, just because I spoke too slowly or too much earlier, but we have more time at these second ones. So definitely, feel free to make me pause a little bit and ask any questions you might have as we go along. So our afternoon hands-on for us are going to focus on implicit and IMEX time integration. We're going to try out a number of things with using a diagonal implicit Runge-Kutta method and an additive Runge-Kutta method that's IMEX. And then we're going to, at the end, maybe in about 10 minutes, we're going to look at some preconditioning and how that affects these kinds of things. So, all right. So I'll note that none of the things that we're going to be doing together really need to use MPI, though all of this could run with MPI. So if you have a node reserved, you feel free to run these things in parallel if you'd like. But I'm going to be just running them on the login node. So. The longer part of our session this afternoon is going to focus on implicit and IMEX time integration. And so specifically, we're going to talk a little bit about what's required. If you're already using, say, sundials or PETSI or Trulinos to do the time integration, there's not much more to be able to use an implicit solver on top of as opposed to an explicit solver. So what are those basic components you need to tell us about? We're again going to look at fixed time stepping, to look again at the stability question. We'll turn on adaptive time stepping. And then we're going to try out 2 different nonlinear solvers. So I mentioned in the overview slides that two basic classes of nonlinear solvers are fixed point-based methods and Newton-based methods. And so we have both classes inside of sundials under the hood. Newton is the default, but we'll turn on the accelerated fixed point and kind of see how that works as well. And then we'll look at IMEX partitioning. So how do we do implicit, explicit, that sort of thing. So the first thing, just to kind of mention, when we have an explicit solver going on inside of sundials and we want to use an implicit solver, there's very little we actually need to do coding-wise. So the first thing is that we didn't look at the raw code itself, but when you create the R code solver, you just tell me what the explicit and implicit right-hand side functions are. So if it was fully explicit before, now you just move that function pointer one argument in the argument list, and now we're going to treat it as a fully implicit problem. For IMEX, you'd specify an implicit and explicit as separate different function calls to be used. If you want to use the default Newton solver, don't do anything else, because that'll be used automatically, but it will require you to say what kind of linear solve you want to happen under the hood. And there's a bunch of them built in. In this executable, we're using an unpreconditioned GMRes. And so just a standard Krylov iterative subspace algorithm, and kind of seeing how well that performs for this task. Though we have other things built in as well. And then if you want to do something other than Newton's method, you would specify that as well. So say, don't use the Newton default, use this fixed point as well. So if you want to see where these things happen, all of this stuff is in hands-on2.cpp. And every one of these things that I've kind of highlighted here, I have a comment right here. It says updated from hands-on1. And if you search for that string inside of the file, you'll see the only changes that were required to go from explicit to implicit between hands-on1 to hands-on2. Okay? So in order to look at linear stability again, let's go ahead and run. Well, I'm going to make this make plot clean. I mentioned this before, but this make plot clean will clean out all these PLT folders if you don't want them lying around anymore. And so we can run hands-on2 with its input file inputs2. Now, remember when we did the explicit method before, it used a fixed time step size of 5. And so I set the default for hands-on2 to also use a fixed time step size of 5. And so it's using this fixed time step size of 5 like before. It takes significantly longer to run. One thing to note, when we use an unpreconditioned implicit solve, we have to do more work per step than when we have an explicit method. So it's taking a while longer. We're also running with the exact same step size we used with the explicit method, which if you could get away with just using this time step of 5 for the explicit method, you wouldn't probably use an implicit method with a time step of 5. But I wanted to start from the same place. So we see that it took 27 seconds instead of 3, which is considerably more heavy. But that's because at every step, it had to do a number of implicit solves. Each one of those needed Newton's method, and each one of those Newton methods needed this GMRes iterative linear solver. And so there's a lot more happening under the hood. But as a programmer, you didn't have to do it. The code was already built to do that automatically. Okay? But now that so we can check the error again. So we can do our fcompare. And we see that this had an error of about 10 to the minus 8, which was essentially very similar to what happened with the explicit method with the same fixed time step size of 5. But now that we're using an implicit method, yeah.
Can you increase the font size, please?
What's that?
Increase the font size.
The font size. Okay, yeah. Is that better? Is that better? I can get bigger. Is that okay? All right. The window over here as well? That's okay too? Okay. All right. So now, 2 times 10 to the minus 8. Is that better for you guys in the back? Yeah? Okay, good. Okay, so now that we have an implicit method, we can try to push for larger time step sizes. And with the explicit one, we tried with a fixed time step size of 100. And so we can try that again. Previously, that ran really fast, and it gave errors in the order of 10 to the 98. It still runs relatively fast. It's only 6 seconds as opposed to 27 seconds. And if we look at the errors that resulted from it, they're in the order of 10 to the minus 5 now. So we get stability by switching to an implicit method over an explicit method. It still has a lot more going on under the hood, and so this is a basic question. When do you use an implicit versus an explicit method? There are going to be more calculations that happen with an implicit method, but you have this freedom that you didn't have before about the time step sizes you want to choose. We see that a time step size of 100 still gives us pretty good accuracy. So you could try even larger ones. Now, I'll note that this is an unpreconditioned GMRes solver. So at the linear solver level, we're doing some pretty naive work here. And so the next set of lecture and hands-on stuff that's talking about scalable linear solvers will be pertinent. But for now, feel free to run with even larger time step sizes than the 100 that I used here. And at some point, so stability won't be an issue, but at some point it won't work anymore. And that's going to be because this unpreconditioned GMRes is just not up to the task of doing, say, a 10,000 second time step size that runs the whole thing in once. But please try a little bit and see what you can get to where you still have a decent error that with these fixed time steps that is stable and the solver actually still completes. Does anybody run with 200? 200 was too big? Well, I mean, was it too big for the solver to solve, or was it too big of an error?
Too big an error.
Okay, so yeah, but it was still stable, I guess, at that step size. Anybody try anything larger than 200? 500. 500? Did the solver run? Yeah? But probably the error was a little higher? Yeah? It's interesting, the psychology of what is too much error. So it depends on who you ask. Mathematicians don't like errors larger than, say, 10 to the minus 16 often, but a lot of other scientists who I've worked with, if the error is smaller than 10 to the minus 1, they're pretty happy. Engineers too, yeah. So, it kind of depends on your culture, but civil, yeah. Well, not just civil. Lots of engineers, like 3% error is pretty good. Okay, anybody get a time step size where the solver just was incapable of handling the system? 10,000? Anybody try that?
510 doesn't work.
5 to the 10?
510.
Oh, 510? Oh, so 500 worked, but 510 didn't work. So that's a pretty interesting threshold. Okay. I didn't try to see exactly where the unpreconditioned GMRes fails at doing this stuff, but yeah. So there you go. Okay. Now we can turn on adaptivity instead of using fixed time stepping, just like before. We stop telling it what step size to use, and we let it run by itself with the default relative and absolute tolerances. And this is quite quick, 4 seconds. It took 133 time steps. Let's look at that. Let's run that process on the hands-on 2 diagnostics file to have it compute the statistics of the time steps that were used and give us the plot of what happened. Because there's going to be something a little more interesting about this time evolution history plot than we saw before. Okay? Though again, we have to wait for it to run. So here, the average time step size that it used was 75. The maximum time step size was 135. And we look at this at the plot. I guess I just need to use display. We see that there were no failed steps when it went. When we did the time adaptivity, it didn't come up with a solver convergence failure, and that probably is because it never tried to use a time step of size 510, I guess is what you guys noted. It rapidly speeds up, like we just saw before with the explicit calculation, but now progressively it's able to take larger and larger step sizes. Anybody have any thoughts as to why say the average step size is going up as a function of time when we run this one? I guess there's a little Google thing you can fill in your answer. But if you want to just raise your hand and say what you think, why it's able to take larger step sizes as the simulation proceeds, we can be a little more interactive. Yeah? The solution is changing more slowly. Remember, this is a drop of poison or something in flow, and it's advecting, but it's also kind of diffusing out and oozing. And after a while, it's just going to be oozed out to be completely flat. Right? And at some point, you could take time steps that are, insanely long, and the previous time step solution is the same as the new time step solution because you've reached a steady state, right? And so what we're really seeing is that with adaptivity, it's allowing itself to ramp up that time step size to track the dynamics of the problem in a way that you could never do by using fixed time step sizing on your own, right? Because you just say what number you wanted, and it would either be too big of a step size here at the beginning if you chose, say, 100, and you'd have an inaccurate answer, or at the end, it would be too small of a time step size because you could have taken a bigger one and still been accurate. go ahead and try out a different relative tolerance, say 10 to the minus 1. It only took 27 time steps to get to the end, so significantly faster. We can look at this, display these plots again to see kind of what happened under the hood. So here the average time step size that it took was 392. It tried them as large as 949. And when we look at the plot of the time step history, if it ever displays, we have a similar kind of behavior, that it ramps up very quickly at first to find essentially the dynamical time scale for this error tolerance. And then as time goes on, it can end up taking larger and larger step sizes because we aren't asking for that much accuracy in our solution. Now, if we actually look and see how much error there is in the solution, we can do this F compare. And we see that it was better than 10 to the minus 1. It was about 3% error for all of the engineers in the room. So we were able to get there rather quickly in an adaptive manner. And we had the freedom to take whatever step sizes we want because we were using a method that's stable for all of these kind of time steps. Is that OK with everybody? Any questions? You guys good with that? OK. OK, so all of this was using a Newton nonlinear solver. So this, I think of Newton as kind of the sledgehammer of nonlinear solvers. It's really powerful. It's heavy because you have to solve big linear systems at every time step, at every stage, implicit stage of every time step. People like fixed point solvers because they're super cheap. It's like they don't do much at all at every iteration, and they take a lot more iterations, but they're so cheap they could be overall more efficient. And so we can turn that on by just telling it that we want to use NLS method equals 1. And so that's going to turn on the accelerated fixed point. It's not a regular fixed point. It uses this process called Anderson acceleration to accelerate the convergence of the fixed point iteration itself. Now, I'll note that the default before had always been to use only at most three nonlinear iterations, max iter, 3 nonlinear iterations per implicit solve, because Newton's pretty heavyweight. But now that we're using a really cheap nonlinear solver, let's also increase that number of nonlinear solver iterations to, say, 20 NLS max iter equals 20. Because each of these iterations is so cheap, we might as well allow more per time step than we had before. And so we run this way. We see, so here we have this relative tolerance to 10 to the minus 1, absolute tolerance to 10 to the minus 9. And it took 284 steps. So let me kind of find where that was up above. So here's that same set of tolerances. Oops. Oh, that's not the laser. OK. All right. And so this one with the Newton took 133 time steps. And since we're not really doing anything fancy as far as preconditioning or anything is concerned, really there's a couple things to kind of look at. It took 1,993 total right-hand side evaluations in the time integrator or nonlinear solver, and it took 5,300 Jacobian vector products, which is kind of the thing that happens inside of a Krylov subspace method. So if this is what Newton required, 1993 plus 5319. Now, in the fixed point, there's no interlinear solver, and it takes about 6,500 total right-hand side. So they end up having about the same cost. Maybe this is, I didn't add them in my head before, but they're not dramatically different. More of the weight was shifted onto, it took more time steps, so more of the weight was shifted onto the time adaptivity because the nonlinear solver was a little less robust. But it's a cheaper nonlinear solver, and I didn't look before, but this only took 3 seconds, whereas before it took, well, a little over 4. So Also not too crazy different, but this one was a little faster. And so what you'll find often is, and it's going to be highly problem dependent, is some problems really require the rapid convergence of Newton's method, especially in, say, chemical reaction networks and things like that. Simpler problems, like this is just a simple advection diffusion problem, are pretty happy with even these accelerated fixed point type methods as well. So you can kind of try them yourself and see what works best. Now, I'll note that all of this is using a relatively coarse grid, 128. Newton's method, as I mentioned before, can be algorithmically scalable as you scale up the problem. The same is not necessarily true of these fixed point iterations. So it may be, I didn't think about it earlier, but one of the hands-on things you could do tonight is try scaling things up, both with the Newton solver, which should be more scalable, and with this accelerated fixed point, and see if that, what happens when we try to scale up this fixed point solver as the mesh size is refined. Okay, so so all of this has been doing this advection diffusion problem fully implicitly. Okay, and so those of you who have done some time integration stuff before, or who are coming from kind of PDE type solvers, know that if it was just advection, you would probably choose to only use an explicit method, because people don't mind that CFL condition when the time step size is proportional to delta x. They're usually pretty happy with that. But when you have diffusion, the time step size is usually proportional to delta x squared, and most people are very unhappy with that CFL condition on stability. And so if you were just doing diffusion, you'd pick an implicit method. If you were just doing advection, you'd use an explicit method. We've been using an explicit for advection diffusion, so it was really stability limited. We've been using a fully implicit method for advection and diffusion, which works fine. But now we're going to IMEX partition the problem so that the advection is explicit only, and the diffusion is implicit. And we're going to allow the integrator to really focus on the implicit part, focus on treating implicitly the parts that need to be implicit, and treating the rest of it explicitly. And so we can turn that on in this example by using this RHS adv equals 2 command. So I'm going to go back to the original. Okay, and so the idea here is this is going to go back to that 5-second time step size, fixed time stepping, but instead of it being fully implicit, it's going to be IMEX. Okay, and so if you recall, the fully implicit one took 27 seconds before. I can scroll back up to the top and look at the solver statistics that happen at the end when this one finishes. Okay, so it's a little faster, 21 seconds. Something to note here, so let's just note that the number of nonlinear iterations now is exactly 20,000. The number of linear iterations is exactly 20,000, et cetera. Whereas before, at the very top, we ran this same thing fully implicitly. We had significantly more linear iterations when we did it fully implicitly than when we do IMEX. Okay, so note, I mean, the same number of nonlinear, but linear iterations was 30,000 before. And now we've reduced the number of linear iterations to 20,000. Okay? And a primary reason for that is that this advection part is a little harder on this GMRes solver to deal with when it's advection and diffusion together than when it's just the diffusion alone. Apparently you guys are chatting away, and that thing can make my phone being every time. Okay, so one thing that I think would be useful for you guys to do for tonight, I guess, because again, I'm going a little slower than I expected, but is since this has something explicit, the advection is done explicitly, but the diffusion is done implicitly, there's again going to be an upper bound on the stable step size. There will be a CFL condition. And if you can find kind of where that is, we saw before that 100 was unstable for the fully explicit problem. And if you kind of refined it, it was around 30 that was stable. Maybe it was 25 that was stable for the CFL stability limit. But now with just the advection being explicit, that CFL stability condition will be a little potentially more lenient. Maybe you can look and see where that is. Okay, so the last thing I want to touch on, and it's primarily just to preview what's going to happen next, is this idea of a preconditioner. So when you run an implicit solve, be it IMX or fully implicit, and we have Newton's method to solve those implicit systems, but then we need to solve those linear systems. So far, we've been doing an unpreconditioned GMRes. And if you were to refine the mesh and run it again, and refine the mesh and run it again, you would see that that GMRes is not going to be a scalable thing all by itself. It's going to take more and more iterations as you proceed. It's going to make things harder and harder on the time integrator because it's not going to be scalable as that mesh size gets smaller and smaller. That's where a preconditioner really comes into play. And so what we've put in here, I say we, but I didn't actually do any of it, is Don hooked up a linear solver that's part of AMRX, this thing called their ML ABEC Laplacian. And it's a scalable geometric multigrid solver for the advection diffusion, or for the diffusion piece. And so we've used that as a preconditioner. And it's not hard to use. Pretty much you have to specify 2 routines to apply a preconditioner for sundials, a setup and a solve. And even in here, I think we're even doing it kind of in a naive way. Everything's in the solve, nothing's in the setup. But the basic premise is the setup gets ready to solve linear systems based on a current Jacobian. And the solve does preconditioner solves. And so we've got this scalable geometric multigrid solver wrapped inside of our preconditioner solve routine. You can go look at it if you'd like. And then when we just create this GMRS solver and attach it to our code, we just say, oh, by the way, use this preconditioner that we've built for this problem. And so if we run with that, we'll run hands-on3.exe with inputs 3. Now, I'll note that hands-on 3, the default is to use time-step adaptivity, not to use fixed time stepping, because I wanted to drive home the point that we want adaptivity before. It's also defaulting to using IMEX, and so we're going to run it in this kind of way. So it took 8 seconds. It took 171 time steps. There's a lot of extra kind of statistics that pops out of here, but we'll note that when we compare this to what happened if we run the same basic thing with no preconditioner, so use preconditioner equals 0. So it says time adaptivity, IMEX, et cetera, but with a preconditioner turned off, this one only took 3.7 seconds. And so this kind of, so note 9 seconds with preconditioning, 3.7 seconds without preconditioning. So a relevant question is, why in the world would you use a preconditioner? I guess is a decent question you can ask. And so that's for you to think about. And tonight when you're running some stuff, I'll give you a hint. I have you running some scalability things, refining the mesh and seeing how well things work. And there, I anticipate you will rapidly see a trade-off in who's faster and who's scalable in comparison to the 2 approaches. I'll note you can also run this with IMEX disabled, and so we can use it with RHS add equals 1. So this would be fully implicit solve, but preconditioning only part of the operator. Does that kind of make sense? So unpreconditioned means we're not preconditioning anything. Earlier we were doing IMEX with preconditioning, and the preconditioner was perfect for the diffusion, and that was the only implicit piece. And if we run this, then essentially what we're doing is we're running implicit advection and implicit diffusion, but we're only preconditioning the diffusion portion of the problem. So advection is remaining unpreconditioned. This is a standard technique people have used for decades in doing implicit solves, is they precondition the parts that they think are the stiffest, that they like to precondition, et cetera, and they leave the rest up to the time integrator, the GMRes to kind of deal with. And so we can already see it's taking a while. But yeah, so this one took about 29 seconds. And it's not always going to be that way, but it's been my experience that when you match the integrator to the preconditioner, so the implicit part that you're treating, the part that you're treating implicitly with the integrator matches up with the preconditioner, so it's a perfect preconditioner for the implicit piece. That works better usually than just not preconditioning parts of it and treating them implicitly. But of course, it'll be problem dependent, so your mileage may vary. But the point being that there's a lot of things you can play with, and there's so many things that are problem dependent that it's good to have access to a library where you can turn things on and off pretty easily to explore that solution parameter space. So with that, I'm going to leave this out brief for the PowerPoint stuff, but there's some evening hands-on things. I'll be here all day and evening, so we can talk more about them if you have questions. But I've kind of hinted at what they are as we went through earlier. And I'm just going to wrap up with a few takeaway messages. So these libraries, Sundials, PETSI, Trilinos, we provide a wide variety of high-quality, scalable ODE/DAE solvers. While you can write your own, these are also available, and they might have much, much more than you would think of putting in on your own. In general, people convert PDEs to time-dependent PDEs, I should say, to ODEs and DAEs via spatial semi-discretization, and then they can solve the resulting ODE systems using these libraries. And one of the biggest questions we have to ask is how stiff is the problem? And that's kind of this fundamental question that we need to identify our answer to before we pick what type of time integrator we're going to use. Adaptive time stepping, I think of it as kind of a no-brainer, but you'd be surprised how many people never ever try adaptive time stepping. It really speeds things up. There's been a lot of folks we worked with, and it seems like I shouldn't get paid for helping them do adaptivity, but I do. But scalability for these things really requires robust nonlinear and linear solves. And so we've talked about Newton being robust, and next is robust, scalable linear solves. All right, thanks. Questions while they're getting set up? Yes.
Do you have any nonlinear preconditioning in Sundials?
We don't do nonlinear preconditioning inside of Sundials, but PETSI has nonlinear preconditioning in it. And so if you were to use PETSI's time stepping module, and then that automatically hooks into their SNES to do the nonlinear solves, then you could try nonlinear preconditioning inside of that. But yeah, they have it built in. We don't yet, but we're on our way that direction now. So yeah, and I don't think that Trilinos has it, but they have all kinds of crazy other stuff too. So yeah. Question back there?
So I have a question regarding the fact that what's the difference between R code and C code? And
Right. So I didn't give an overview in general, but C vote is linear multi-step methods. So it's BDF and Adams-Moulton. So these are kind of classical things. They have a very small amount of work per time step because they store a whole lot of history of things. And so they're really hard to beat. They're the gold standard of time integrators that everybody races against when they write new methods. R code is a multi-stage method, so it's all based on Runge-Kutta type things. But it allows us to do all kinds of other splitting, so into implicit and explicit, fast and slow for multi-rate calculations, and that sort of thing. So it's based on kind of newer time integrator, newer developments in the math community for time integrators. And it's where most of our new development is kind of occurring. If you have a problem that works well with C vote, it's unlikely that anyone's going to beat it, especially not R code. But there's a lot of problems you can't do fully implicitly with this linear multi-step package. And I'll note one of the big limitations as to why we built a multi-stage method is spatial adaptivity. So if you refine your spatial mesh, suddenly you have a completely different discretization than you did 5 time steps ago. And so a linear multi-step method that wants to use all this whole history to build up high-order interpolations in time can't happen unless you back project everything you've done in the past. And so that's just not really, people don't do that. They just restart the thing and it goes back to first order over and over again. Whereas we can just stay at 8th order the whole time because at the end of a time step, you refine your mesh, do your stuff, project your solutions, and we resume from that moment. And so that's kind of one of the fundamental differences as to why you might choose a multi-stage versus multi-step type integrator. Other questions?
Okay, well, we're
I'm
out of
over time.
But let's thank Dan. Thanks very much.